you guys have your notes open. You're just going to keep passing those correction sheets. There are going to be a few different times when I get you working on problems that I can go ahead and pass back the test. I'll probably do it right towards the end of today. Our goal, remember, we have a test on Thursday, yeah? Nope. Okay. Theoretically, almost could have crammed it for tomorrow, but we decided to spread it out, Mr. J and I. So that we can have a lot more time on 3-5 today. We're going to do lots of examples to help you in homework. Remember I said last night, probably work on a different subject besides Precalc so you can focus more time to Precalc tonight. Hopefully you did so. We're going to finish 3-5, do as many examples as possible to help you with homework. That way tomorrow we can focus on the review. And if some of you guys can peek at the review tonight, that might help in the sense of coming in tomorrow. But we'll have time to work tomorrow. Maybe not on the exact review problems. It's not just going to be a work day because that's not everyone takes full advantage of that. But we'll definitely get to see some key problems that will be on the test. Remember, on Thursday you have to have your spiral and your notes ready to go. Sound good? All right, section 3-5. Let's jump into it. You guys should be almost done. Ashley, you can just put it on the table. Is there any extra? Okay. All right. Yesterday, you guys were supposed to skip me one line each, right? Cool. We got a lot of notes written yesterday. We just didn't get to talk through them as we were going over homework examples. Thank you once again, my volunteers that came up to the board. Here we go. Section 3-5, real world applications, okay? We've been doing exponential, we've been doing logarithms the entire chapter, but now we're going to apply them to just a few different applications. There are tons and tons of them. We're just going to do a few. Number 1 says identify the proper model to use. Either, ready? Either it's been given to you, given in the problem, or you're going to have to identify by the clues. So depending on the problem that's given to you, either they're going to outright give you an equation. That's what a model is. It's going to be an equation that models what's going on. Either they're going to give you an equation, you're like, sweet, all right, fine, I'm using that one. They gave it to me. Or they're going to give you enough clues as long as you read the problem. And guys, careful with our book. Hopefully you've noticed the directions are important. That's why I had you write them. So in a few of the problems in homework, actually, it's going to tell you what to do in the directions. And it might not be right above the problem. It might be like a whole section of problems. And it might be on like the page before. It might be a few problems up. Go find those bold directions and make sure you read them, because either they're going to give you the actual model or equation to use, or they're going to give you the clues, okay? Number 2, identify the variables involved. Whenever you have an equation, you're going to have variables. You're going to have y's, x's. You guys started writing just a few of them yesterday, right? You were writing this one, then you wrote the interest one, which has different variables. There's like a p and an r and an n and a t and an e. Oh, that's a number. Just kidding. And an A, and then you have for these ones, A's and B's and X's and Y's. So we have to make sure we understand what those variables are. So step number 2, coming back, identify the variables involved, which kind of has 2 different components to it, right? Figure out the meanings. I'll just say the labels. And any clues associated with those variables. First of all, you can't really figure out what should be plugged in for those variables if you don't even know what they mean. So you have to look, have the equation, have the model, figure out what those different variables stand for, what they correspond to, if anything. And then go look at what's been given to you in the problem and say, hey, did they give me anything? Did they tell me what to plug in for this or for that? And remember, equations, the variables are always changing. It's true for lots of different values. So if they do give you a clue, it's only for one specific place. It's not for the whole model. It's not for the whole model. And then number 3, finally. Once you've figured out the labels, figured out what the variables actually stand for, and you're able to match any clues with those variables, then number 3 says, hey, plug in different quantities. Plug in what you have. Once you've figured out what those numbers are for, those given values are for, then plug in and solve for what's being asked for. However, one quick note on this one too. sometimes. You need to plug in different values separately. What that means is sometimes they might give you more than one clue from more than one point in time or more than one situation. I guess the situations should stay the same. But more than one data point. And as we know about lines, lines have how many points on them? Just think like mathematically for me, just for a second. A line, how many points? Infinitely many. It goes on forever, right? But to make an equation of a line, do we plug in all the points at once? Doesn't make sense. We usually only need, well, depending on what we have, 2, right? However, depending on what we have, once again, you kind of have to sometimes plug in those 2 points to the slope formula and then plug in 1 point to the equation. We're plugging in separate places. So you're not always able to take all of the information and just dump it in the problem. Sometimes it can't handle it. It has to deal with it separately. So sometimes you're going to have to plug in some stuff to the equation here and then be like, let's just wait. And then plug in some stuff here and then compare the two and say, I wonder if I have a system of equations with multiple unknowns that can somehow do substitution, elimination, something in order to make it work, okay? Just to let you know, just because you have information doesn't mean you can just dump it, right? It's not always helpful just to dump all this stuff. Sometimes you have to deal with it piece by piece. There's a life lesson in there if you think about it, but let's keep going, okay? Exponential growth. First of all, why is it called exponential? Not just because it's rising, lines rise, parabolas rise. Well, half of them do. What's in each of the equations? An exponential function, right? They're just called exponential because they have little exponential pieces, not logarithmic. So it's called exponential because they have little exponential pieces. The growth one is a growing, that's why it's called growth. And the decay one is decaying, or lessening, that's why it's called decay. And question, why would interest formulas be under growth? You put money in, hopefully it's not just the stock market, you put money into some account that's making interest, and hopefully what happens to your money?
You get more of it.
Hopefully it grows. Well, maybe not triples in value. But it grows. Take personal finance, it maybe can grow faster than some of you are thinking. But, right, it grows. Why is it called exponential though?
Rapid, because
That's how like most commentators or something, like whether you're watching like CNN or I don't know, something on the news or someone who's trying to comment on the economy or whatnot. We're talking about like the population boom or whatever. Exponential growth is something they use. It means growing really fast. Yeah. And also exponential growth happens in nature a lot, not just with like interest, but also with like bacteria that's like doubling or like radioactive substances that are decaying or all sorts of things like that. Those are exponential in how they grow. But do you see the exponential piece of this one? There's a t in the exponent. Now this is kind of tricky because there's like variables everywhere. You're like, what's going on? But there's a t. T is actually kind of like x for all of our interest things. And t stands for what again? Time. T stands for time. Now one thing you guys need to circle in this interesty thing, actually I'd say 2 things. A lot of people get confused about who on earth n is. So we'll do an example in a second. Who on earth is n? Number? More meaning than that. And then they get confused and they don't realize whenever a problem says continuously compounding, it's not just saying, hey, guess what? It keeps on making money, which both of them theoretically could. Instead, it's talking about how it's making money. There are different ways to compound interest. You could have an annually compounded interest account. What would that mean if it's annually compounded? Yearly, once a year. Wait, once. How many times per year?
One time.
N is 1. You use the top formula. What if it says something about it's compounded monthly? N would be who?
12.
Per year? 12. How about daily? 365. How about weekly?
52.
52, right? So N is talking about a certain number of times per year. And then you can plug in, if it's annually, plug in N is 1. If it's monthly, plug in N is 12. If it's daily, plug in N is 365. That's something that comes from the problem. But what if they don't tell you any of that annually, monthly, weekly, and they just say continuously? What does that mean? it's always compounding. It's always compounding. If it's always compounding, guess what formula you use? Per. I know, it's a silly way of remembering it, but per. So if they tell you how many times per year, they give you clue words like annual, monthly, annually, monthly, daily, weekly, etc. That's when you use the top formula, but when they just say continuously, you have to look for the wording. That's when you're using per. You guys already got these two graphs. Let's go to that example that we were starting or ending with as you guys were writing yesterday. Okay. Why am I going here? What's it talking about? Look at the title. Oh, making me tired. What kind of compounded interest? Read the directions. Read the bold stuff.
Continuously.
Nice. So what formula from the get-go am I going to be using?
Per happily.
Per. Now, hold on. Before we start this problem, because I could just start like going and plugging in stuff. But if you don't understand what the A and the P and the E and the R and the T stand for, well, it's going to be rough, right? So hold on. Let's think about this interesting thing. Ready? We already talked about T. Who's T?
Time.
Okay. So we know that T is time. Let's go backwards. What's R?
Rate.
Rate. What kind of rate? The percentage rate for the interest. Or the account that's making interest, I should say. What's E? A number. E's not a variable. It's a number, right? 2.71828, etc., etc., etc. What's P? Initial investment. Usually with money, you guys think of it as the principal balance, right? Principal. I think so. Principal? Maybe it's Ellie.
One of the two.
They're both nouns, aren't they? I should know
Oh, it's
this.
principal.
Ellie, right?
Yeah. Principal is principal.
Yeah, your principal is your pal.
Yeah.
Pal.
No, yeah, right. It's like Mr. Halliday, but it could also be
These are
the
pal.
foremost.
Pull.
But I think this one is pull. You're right. Okay, no excuse for bad grammar even in math, but now we're back. A. Amount? Well, isn't the principal an amount? Final amount. Or amount after a certain amount of time. I'm going to say amount after T, which could be T years, T months, T days. It just depends on the problem. Okay? All right, with all of that, let's come on down. Remember the idea that you don't necessarily take all the info and dump it in at once. That's going to be maybe a little bit too much of an overload. All right, what's something we know?
P and R.
P and R. So, A, not really sure what's going on. P, I know is $750. And then R is, oh, okay, 10.5, right?
No.
No! What do you do whenever you see a percent?
Make it a decimal.
Wait, no.
Move the decimal place 2 places to the left, right?
Yeah.
Move the decimal place 2 places to the left. You guys have seen the nasty numbers. Yes, please. You have that calculator. Good idea. All right. The main thing is with this one, the clues went in really nice, really easy. And guess what? All we're missing is T, which is like X, and A, which is like Y. So this is actually a really good plug-in in the sense that we've gotten rid of all the extra variables. But now we have to answer 2 questions. How long does it take to double? How long does it take to double? And how much do you have after 10 years? Now, how long? I'm going to find T when? What does it mean if the amount doubles? Who gets the who?
The initial investment.
The initial investment is now doubled. So who is double the initial investment?
15,000.
Okay,
A.
1,500.
A.
Sorry.
But who is 1,500? A.
A.
Right? The amount you now have, that's A, is 1,500. Oh, so when A is 1,500. Now we'll do this in just a second, but that's one question they're asking. What's the other question they're asking?
When time is 10.
Find
T.
A.
Sorry, A.
A. Good. When? What's the clue?
T is equal to 10.
Now, you can imagine this could be a little confusing if you just opened your book, turned to your homework, saw this table, and was like, say what? But now that you have the clues, can you guys use the equation and try to solve for them separately? You can't do it all at once. Separately. Take your equation. What are you going to do with this clue?
Plug it in.
Plug it in, solve. What are you going to do for this clue?
Plug it in.
Plug it in, solve. Ready, set, go. Use your calculators. I'll only give you like 60 seconds head start, and then I'll come behind if any of you stuck. But you're just plugging in what you know and solving for what you don't. For the first clue, plugging in what you know, solving for what you don't on the second clue. Let's see how far you get. I'm using this model. Should get my calculator too.
Oh, you didn't plug it in.
I'll show you the work that gets there in just a second, but I have the answer waiting just in case you want to see. And second answer waiting just in case you're ready. I'm coming back to fill in the pieces just in case you need a little extra. Just something went wrong. I know, the air turned on me. You guys agree with my first answer, ln of 2 over 0.105?
Yes.
Let's take ln of both sides to undo that e, then do a quick division. I rounded to 3 decimal places because I've mentioned before I always like 3, it's getting me ready for calculus. Although the next one I only rounded to 2.
Money.
It's money. So money, well, there's some people that wouldn't mind lots and lots and lots of tenths of cents, but gas stations? Anyway, coming back. This one, all we have to do is, right? But most people, you're right, would not. For those schemes where they like skim off an indistinguishable amount from all these different accounts and then it compiles to be quite a bit. Maybe that's just a movie plot. Anyway,
Let's do that.
you guys agree with my second one? 2,143.24? Hey, I'll take this account any day, right? It's not very realistic these days, though. True. It's called saving for your future.
It's still
The
10.
interest rate now is 0.001.
You also only put in $750.
Yeah. So that's 700.
So if you keep contributing to it every month, then you're contributing more, it's growing, and it's compounding interest. That's personal finance. Anyway.
That's
I wish I had
$750 today, and 26.
Yeah, like
$2,000.
0.01. Anyway. Most accounts that have high interest rate, the money is locked in there. Like a mutual bond. Ready, set, the clues have changed. The question is the same. The clues have changed, but the question is the same. Meaning, what are we still using? A equals per. What does A stand for? The same thing I did a second ago? How about P? Same thing. E? Definitely same thing. R and P? Mm-hmm. But this is for a different situation. Same amount of money that you're putting in, but situation has changed. So we still know the following. You don't have to write this whole example, right? You're literally just saying, hey, new example, same exact stuff to begin with, though. We still know that this column is P, this column is R, but uh-oh, he's missing. This column is still T when A, the amount is double whatever the P is, which is going to be 1,500 again. And then this one is A when T equals 10. And guys, all of that is from reading, understanding, comparing to the variables up above, and trying to put it kind of in like math speak. Kind of like double speak, but not 1984. We kind of just have to plug and chug and see what happens. It's not as straightforward as before. We don't just have P and R. We really want an R, we don't have them. So, well, let's plug in what we do know.
Okay.
Okay, so we have A is equal to 750, just in general, e to the RT. That's my general equation. That's all I've got in the sense of what I can plug in. That's true all the time. The only things that are true all the time is how much you initially invest and the rate, and everything else, well, it changes based on the other two. Okay, what can I do for that time to double? I mean, there's a number in there. It's kind of important, right? I know T, right? So I can plug in e to the R times 7. I'll just go decimal since we're using our calculator anyway. It's fine. You got me to write a decimal. But then coming back, is there anything else you can plug in? Oh, 1,500. That's right. Because if I have P, then I just need to double it in order to plug in. Okay, double it. There we go. Can we solve for R?
Mm-hmm.
Nice. We need to find him anyway, so we need to fill in that blank. So I'm going to go ahead and go quick, just because you guys just saw me solve for one similar. We were actually solving for T a second ago, but it's in the same spot in the exponent. We end up with e to the 7.75 times R. ln. Is someone ahead of me and get me an answer so we can keep moving? Ooh, give me a few more decimals. Start at the beginning.
8.943.
And is it 0.0 technically?
Yeah.
Okay. So if you were just to plug and chug into your calculator, 0.08943, and then they went to percentages. Why? It says make it a percent, which means move the decimal 2 to the right. And so R is equal to 8.9.
8.9%.
And if I was to do my whole like little decimal thing, like keep the 3 like I like, I would go to 8.943%. All right, now we got one blank filled in. So what do I do for the next one?
Plug in all of
Separately. Yeah, take what we already had, plug in what we now know, and then plug in what else we know. Right? So do we know A? Nope. Why? Well, we're finding A. We can't know A if we're finding it, right? Equals P, 750. Got it. E, he's just a number. R, I found him, 0.08943. T. Oh, look at that. Plug and chug. Throw him straight to your calculator. He's ready to go. I have the money sign awaiting. Ricky and Justin and Maddie are going for it. A few others. Let's double check each other and see if we got it.
1,834 and 22 cents.
1,834 and 22 cents?
22 cents, yeah.
Hold on. Back him up.
Yeah.
That's good, good, good.
Yeah.
The table's a little daunting unless you just take it piece by piece and then you say, oh, alright. Now the nice thing is, guys, haven't I kind of already went through and talked about what each of these columns is doing or behaving or acting or how to plug in? That's what's helpful. That's what I'm talking about at the very beginning when it says in the steps to solving these models. Figure out an equation, which we did, right? From the keyword continuously compounded. Identify the variables. Figure out who is A, who is P, who is R, who is T. E is a number. Forget him. I mean, use him, but don't worry. Figure out any clues associated with the variables. That was my read it and then try to put it in the variables. A equals, P equals, T equals. Find T when. And then plug and chug as much as you can. Remember, you can plug in separately like we kind of did for each. We had to plug in the clues separately in order to solve. Okay. Uh-oh. Life just changed. Hold on. Write down the information that you have.
Oh, I
Half-life. Uh-oh, something's decaying. Write down what you have.
We did this in
Write down your clues. We're going to use them in a second. Trying to see their actual directions so you guys can get some context. Radioactive decay. Complete the table for the radioactive isotope. Well, they didn't tell me anything. They did. Radioactive what?
Decay.
Decay. Wait! There's a model for that. Isn't there? Decay. Y equals. Now, hold on. Usually we'll put X, and this can apply in many different circumstances. Hence why that formula was really general. But looking at this, what was X with all the interesty stuff? He was actually a who?
Time.
T. Does this one have time too?
Yes.
So I'm going to go ahead and make it
T.
T. Sound good? Because the X can be a T can be an X, etc. Alright, because we have time. So hold on, let's talk about a few things. Can anybody, just by thinking the money example, and A equals PERT, can anybody figure out what variable this initial stands for?
A.
Uh-huh.
A.
It's the same spot as it was a second ago. So let's make him A. It was P for PERT, principal, etc. We don't really say principal for radioactive isotopes, but if it wants amount after 1,000 years, you guys see the when T equals 1,000, right? But who are we trying to find? Which variable are we trying to figure out?
Y.
Y. The amount. This one, that spot. So we can use what we knew about the money example and apply it to an example that doesn't have to do with necessarily the PERT equation, but an equation that behaves very similarly to. Half-life. Did I know what a half-life is?
Nope. What's
What's cutting in half?
It's the half of the life. It's the entirety. That times 2 is the entire life of the
The
isotope.
mass is being cut in half because it's decaying, so it's getting to only half of what it was before. And the 5,715, well, that's not half of what it was. So this must be,
B.
no,
Y.
no.
What? Easy number.
Easy number.
A.
Well, we're running out of things that could be.
Years?
A half-life is how long it takes for this isotope to decay. Carbon takes a long time to decay. Oh, I think there's actually a thing in science about that. Anyway, coming back. My science people, we should be like, oh yeah. This is T. So this is T when, not find T, we're given T. It's T when half-life. Who is half? The amount you have is half of what it was to begin with. Which is kind of like in the last one, the time it takes to double. The amount you have is double what you started with. This one is the amount that you have is half of what you started with.
I'm confused.
But the T
Yeah.
is there.
I'm not teaching a biology lesson necessarily, or even a chemistry lesson. But I'm just talking about, I'm telling you, teaching you, reminding you, maybe. Half-life is the amount of time. I'm teaching, I'm telling you. I'm not saying you had to know this before you walked in the classroom today. Some teachers might be ashamed that you don't. But the half-life is how long it takes, time, how long it takes for the amount to be cut in half, to decay to half of what it was. And so if this is what you have after a certain amount of time, then Y is going to be half of what you started with.
So if it's amount after 1,000 years, what would that be?
Yeah.
Because if that's T, then what's amount after 1,000?
Well, 1,000 years isn't 5,715 years, right? So it takes this long to cut in half, so it must be something in between 6.5 and half of 6.5, which is 3.25. I think 650 cut in half, $3.25. So it has to be something in between there, because it's definitely not gotten down to half. It's still something pretty close to probably 6.5. Does that make sense? Okay. Now, with that, remember, sometimes we solve things separately, right? Not all at once. So we're going to have to solve maybe separately. But hold on. What can we plug in? That's kind of like the end of the problem, right? Fill in the question mark. All right. So what do we know? Let's start with our big model. Our big model is y equals, what's the true, or what's the same no matter what year it is from the beginning?
6.53.
We always start with 6.5, right? The beginning is, your initial amount is 6.5. E stays the same, he's a number. Negative, I don't know who B is, and T changes based on 1,000 years, 5,000 years, 2 years, 10 years. I'm just saying T changes, so I'll just keep him a variable. B, I don't really know the rate, if you want to think about it like that. So this is my beginning model. I start with the decay, I plug in the initial amount. All right. Now I say, given this column, now this one, guys, this is just the name, right? No big deal, it's just identifying who this is. No numbers to plug in, we're not putting carbon 14 in there at all. We're saying it's for him. Okay. What can I plug in for this one? I can plug in T, so I have 6.5, e to the B, I don't know, there's no B anywhere. All right, 5,715. Anything else I can plug in?
Oh, 2B.
1/2.
2B. No,
Not
2.
2B.
Sorry, 2Y.
Divided by
1/2 times 1.
2B, 2Y. Wait, 1/2 times Y?
Y. The Y
Oh,
is 1/2 what you had, right? The amount after 5,715 years is half of what you started with.
Can't we just change
Yeah, and who is half what we started with? You talked about this a second ago. 3.25. Remember, I start with 6.5. I now have only half of that left because the rest has decayed away. Not that whoever was there at the beginning is still there at the end to measure this, but divide by 6.5. Oh, now we're just solving, right, cool kids? It's an equation, no big deal. Solve, solve, solve. This is going to end up being 1/2. Well, that makes sense because it was a half. Never mind. Equals e to the negative 5715b. You guys saw us do this a second ago. What do we do to both sides to solve?
Line.
Yeah, we need ln, we need ln. Divide by negative 5715. Pretty sure this number is going to be pretty stinking small, right?
0.0012129.
Double check, did I get all the numbers? 3 zeros?
Yeah. Oh, 12129.
Ah, thank you. Everybody back them up? Usually math, if someone else gets the same answer, we're probably going in the right direction. I'll do it. 5, 7, 5. And then remember, what's e to the negative 4 mean? Scientific notation times 10 to the negative 4, you move the decimal places.
To the right.
Or
Left.
to the right?
Left.
Yeah, you're right, sorry. Your left, my right. Just for sake of illustration. Yeah, go this way, make it smaller, right? Hence why Wiki was able to say 0.000121. Now we have B. That's a good thing, right? Because we're not done, but at least we have another piece of the puzzle. Can't we plug that in? Y equals 6.5 e to the negative point 0.0012129. That's rounded, that's okay. Huh? You could, but remember we would change it to a percent and then change it right back to a decimal and plug in, so it's like, They didn't ask us to fill in a box with the percent, so we just left it a decimal. Wait a minute. Is there anything else I can plug in for my box?
Yes, 1,000.
Nice. T is 1,000. They're asking for the amount, the Y, after 1,000 years. So once we figure out the B, once we figure out the rate, we can just plug and chug and then solve, solve, solve. I'm going to double check with you guys. 6.5 times. You guys are probably putting the rounded version here. Sorry. Let me put that one in too. Anyone?
5.757.
And if I'm doing my 3 decimal places, I'll do 5.758. Who? Grams. So David, it didn't quite get to half, huh? But do you see how my logic kind of helped? Because it's like it was 6.5. It takes 5,715 years to reach 3.25. It must be something in between, closer to 6. Well, 5.7 something. That's closer to 6. It makes sense. It makes sense. Now, kiddos, was this a little bit harder than the money one? Probably, right? Because number one, I didn't have a PERT equation to plug into with nice little meanings. And number two, half-life, we had to figure out what that even meant first. But why do you think I did this example in class?
Because it's the hardest.
Well, so we can work out what it means before you go and practice it on your own. Does that make sense? Okay. Remember, this is a math class. We're trying to figure out how to apply math in order to solve other problems in other fields. So we dabbled a little bit, right? A little bit in science today, but don't stress. We worked through it together, and then we kind of just saw how to put the math in and how to solve. We're helping out some of your science teachers, both in high school and probably in college. So let's keep going. Ugh. There are more models than exponential growth and decay? Yes. But the good news is, these ones I'm putting in parentheses, because even though you might play with the equations just a little bit, I know you don't think it's playing, but even though you might work a little bit with equations in homework, I'm not going to make you come up with these equations on your own. I'm not going to ever make you on the quiz or test, or even in homework, you have your notes with you. I'm not going to make you memorize the equation, come up with it off the top of your head. You're probably going to be given this one, and you're just working to figure out how to plug into it, okay? So I'm putting these in parentheses. They're not to be memorized for a test. Remember, don't stress about the equation. Just give me a quick little, oh, hey, it's a bell-shaped curve. Ooh, statistics. Oh, it's a division sign. Sometimes in math, when expressions get a little bit complicated, it's easier to show it like this, just in the sense of quickly typing it, than show it the other way.
Oh, so
With programming and whatnot. But it means like all over C. That's what it means. If you want to write it this way, it's probably a little bit better.
so it's not 2 divided by C.
It's this whole negative x minus b squared, all divided by c. So maybe it's better to write it that way. It's a bell-shaped curve to get a quick little sketch. Logistic growth, he's pretty stinking important. We'll see in application we have a problem with him, just to show you, okay, these are ones you don't have to memorize the equations. You don't have to come up with all this crazy stuff on your own, like with the interest and even with the isotopy one. Maybe I shouldn't call him isotopy. Anyway. But these are ones you might still see in a problem in homework and have to work with, but it won't be as difficult. Does that kind of make sense? A little bit? Couple more seconds, but we want to get to an example where we can use him. There is technically one more model. After these two. Once again, it's not one I would make you come up with on your own. The equation's going to be given to you. Just to remind you, this is another model. We talked about exponential, both growth and decay, because it could be a vertical reflection. Sorry, horizontal reflection. There's Gaussian, there's logistic growth, and then there technically is one more model that involves logs and or exponentials. But he's not really that special in the sense of he's not as widely used as exponential growth and decay, so I'm putting him in parentheses as well. But I want you to get the general shape to remember, oh yeah, logarithms, they're the ones that have a vertical asymptote and then swoop up, right? And basically, what's the long story short? It's an equation with a log in it, that's all. Nothing snazzy. It's an equation with a log in it. Nothing too snazzy. Okay. So logarithmic, just the two different equations, usually a common log or a natural log. We're not saying there can't be any other type of log, but those are the ones that are normally used if we're modeling. Because the quicker ones, the easier ones. You guys have seen me use ln a lot. And don't worry about the equations. Remember, just get a quick little swoop and say, oh, okay, that's right. That's how the equations generally behave. We almost there? Okay. The next 2 pages are going to be 2 different word problems. We'll get as far as we can on them. But I want to counter the idea that just because a problem has tons of words, it's naturally ridiculously hard. Come on, you think it. You turn there and you're like, oh my goodness, skip that one. See if she does it for us tomorrow. Okay. No. True, right? Just because a problem has words doesn't mean it's ridiculously hard. We just saw two different types of problems that were actually really stinking short. There was a table with numbers, and they were kind of hard, right? Let's check out words with words and see if maybe we read it, we get the idea, maybe the solving isn't too bad. Like, stop. You heard already my goal. Ready? Okay. Estimates of the amounts in millions of dollars of U.S. online advertising spending from 2011 to 2015. Data. Go. Okay. Money's being spent advertising online, obviously. A scatter plot. Okay, cool. They put points in the scatter plot. The little breaks just mean like, hey, lots of the graph is missing. And they give us a, oh, hey, looky there. They already made the model for us. Sweet. S is the amount of spending, and they're telling us what the variables are. It's a good day. T represents something to do with years. That makes sense. At the bottom, compare the values given by the model with the estimates shown in the table. Okay. So if I plug in 11, it's going to be closest. 12, closest. They're saying, remember, even though this data is here, the scatter plot is here, an equation is the best approximation. But then they say, according to this model, when will the amount of, oh, finally, there's a question. When will the amount of U.S. online advertising spending reach 80 billion? Put that in math. Who will reach 80 billion? S. When means find. T. When S is 80. Billion? Exactly, that's the label, 80. Oh, really? What do you do to solve the problem that was represented by this whole huge page? 80 equals 9.30 e to the 0.1129t. Solve. Whew, that was rough. Wait. Spending is S. S is 80. Plug it in, divide ln, both sides, you're done? Yeah. Check. Right? Not bad. True? Okay. Another one. That's a whole blank page to work on it, but we didn't need it. Oh, man. This is one of those nasty logistic growthy ones. It's one of those nasty ones where you're going to have a little swoopy swoop, and the little swoopy swoop is going to start down here, and it's going to like grow really fast, and it's going to taper off at a horizontal asymptote of 5,000. Why would, what's going on? A college campus of 5,000 kids. One student returns from vacation with a contagious and long-lasting flu virus. Really happens. Oh, college, yay. The spread of the virus is modeled by, happens here too, right? Someone gets sick and then suddenly everyone's sick. The spread of the virus. Why would the virus go really quickly and then taper off? Why would it just keep going?
Because a lot of people are already infected. They've already got them all.
Because you have your community. It's 5,000. And we'll assume the teachers are like, after a certain point, we're staying home. And then we'll say the community is like quarantined. They're like, fine. There's only so many kids that can get sick on the campus, right? Okay. Virus spreads and then it tapers off because there's only 5,000 kids that can get sick anyway. Where? Y is the total number of students infected after T days. Okay, so we have T already. We have Y is the total number infected. The college will cancel classes when 40% or more of the students are infected. Letter A. How many kids are infected after 5 days?
No test today.
Find Y when T equals 5. Wait, what? T is days, 5 days. What are we going to do? Plug it in and plug it all in our calculator. Hold on. What's going on for B then? After how many days, find T, will the college cancel classes? When? Hold on, this is kind of hard. How many kids are sick if the college is canceling classes? 40%. So Y has to equal 40% of. He's even dabbing so. Plug it in. Plug it in. Kiddos, when you get to homework and there are words, read it, match the clues with variables, plug and chug carefully. Ah, your test.
Hi.
Do you guys want them?
Yes.
All right. My college name, come get them. If you don't want them, just go ahead and leave. I'll give them to you tomorrow. Justin, Jane, Amy, Lauren.
Hold up, hold up.
All right, Jason, still here? Jason.
What'd you get?
I'm
not telling you until you show me your better or worse grade.
Naomi. Nadia.
I'm gonna get better grade.
Jesse.
Go quicker. Be cold quicker, Caleb. I need to go.
Ricky.
That's great. Thanks.
Maddie.
I got two.
Alex. Austin. Jacob.
What'd you get, Tyler?
Snicker, snicker, snicker.
94?
Lucas. Scott. Elaine.
Triggered.